So let's just take this little detour just to look at conversion. Remember we said with that inner constructor when we created our type, there was this convert function. In our example, it converted integers to 64-bit floating point values. So let's look at this convert function. I can say convert takes two arguments. I want to convert to this type, float64, and I want to convert this value 10, remember, which is just an integer. And we're going to get back 10.0, indeed, a floating point representation of that integer. Now, if I were to say convert here to integer 16-bit integer, the value 10.1, I'm going to get this inexact error that is thrown because we're going to lose some information here. I cannot convert a floating point value back into an integer because we are going to lose a bit of information. If I were to pass 10.0 though to a 16-bit integer, it will return the value 10. So the convert function will try its best without losing any information to convert a value from one type to another. Then there's the promote function. I'm going to say promote 10 and 10.0. And what is it going to do? It is going to look at, let's call it the smallest possible type representation of all the types that you are given. And this really is what is under the lid of multiple dispatch. Because if I have a function and I pass two different type of arguments to it, it's sort of got to look at how it can, which of the methods it's going to use, and can it use this kind of promotion. Now, I cannot convert down to it won't allow me to convert, or it won't convert these into integers. The smallest sort of level of types that can hold these two values, this integer and this float, is going to be two, to make them two floating point values, so 10.0 and 10.0. And indeed, if I looked at the type of 10, that's 64-bit integer, and 10.0, that's a 64-bit float. So it is going to promote this 64-bit integer to a 64-bit float to hold that extra information. And a lot of this is what is happening behind the scenes with your inner constructors of creating your own types. Let's have a look at parametrizing a type. Now, we've created a type before. We had these fields, and these fields held a certain type, and that all formed part of our type. I'm going to introduce this new type. So I'm going to use the keyword type. I'm going to call it vector underscore 3D. And then inside of these curly braces, I have this placeholder uppercase T. That's by convention, we use T. And it has three field names, X, Y, and Z. So imagine I'm creating this type to hold vector valued functions in three-dimensional space for me. And I say that this type must be, of all three fields, must be of type T. And what this T placeholder is doing is it's saying you can pass any type to these fields as long as they're all the same. So I've created this parameter, hence the term parametrizing your type. I've passed this parameter T so it can hold any abstract or any concrete type as long as they're all the same. So let's create this type. So we have a brand new type now. I'm going to use a computer variable called vector underscore 2, and I'm going to pass this values 10, 12, 8, and notice that all three of them are integers into my new type vector 3D, so it's going to be of this type. And it actually tells me now that they were all 64-bit integers because it wasn't specified here. So when I pass these integers, then this T, then we actually declare a type for this placeholder T. So if I pass something like 10.1, 10, and 8, we were going to get this error. Convert has no method matching a 64-bit float, which 10.1 was, a 64-bit integer, and another 64-bit integer, which the 10 and the 8 was. Because of the parameter I set here, they all have to be exactly the same. Otherwise, I can't instantiate this type. I cannot create an instance of this type as I tried to do here with vector underscore 2. I passed three of the same types as values there, and that actually worked. Now we can constrain this parametric type a little bit by this notation. So it's still parameterizing this new type of mine called vector underscore 3D underscore real. So it's still this parameter TTT, so all the fields actually have to hold the same type, but now I'm constraining it that this value must be of one of the concrete types that are subtypes of the supertype real. Now, one little thing I just want to make you aware of, I used a different name. Up here, we've got vector 3D as our type, and I've got vector 3D real. And the only change I made was just constraining this parameter. If I were to try to recreate this vector 3D, I'm going to get an error, invalid redefinition of constant vector 3D. So once you've created a type, you cannot recreate it. You can't change it in any way. You can create an instance of it, and if you use the keyword type, you can change the values. If you use immutable, you can't. But I cannot recreate. Once I've created this, I have to stick with it. If I made a little mistake, I can either clear the whole workspace by using the keyword workspace, open close parentheses, but then you lose all the values of your user-defined types and all the values in computer variables that you've created. So I have to use a different name for these, otherwise I'm going to get this redefinition error. And now I can instantiate this new type. I can create an instance of it on an object. I'm going to call it vector_3. And it says 3D real is not defined. Now, what happened there? I think what we didn't execute this line. So now my type is created, and let's instantiate that. And lo and behold, we get vector 3D. Once again, because these were all integers, I passed integer values to them, and actually tells me now that these are 64-bit integers for my parameter, which all three of my fields now carry as a type. Next up, we're going to look at the equality of values. We just have to make sure that we understand that concept.